Our galaxy, a place filled with countless mysteries and wonders beyond our wildest imaginations. Created from what seems to be nothing, our galaxy is just one among potentially hundreds of millions we haven't yet seen. Floating in the vast universe, these galaxies, each with their own secrets, all share one unanswered question. How did they form from what appears to be nothing? The universe, an ever-expanding mix of galaxies, stars, planets, and myriad forms of matter and energy, presents a profound mystery that has captivated humanity for centuries. At the heart of modern cosmology is the understanding that the universe began approximately 13.8 billion years ago with the Big Bang, a colossal explosion that marked the inception of everything we know. This event set into motion the expansion of space, creating the cosmic web we observe today. Scientists have gleaned much about the universe's composition, revealing that ordinary matter, the stuff making up stars, planets, and us, constitutes a mere 5% of the universe's total mass and energy. The remaining 95% is a mysterious concoction of dark matter and dark energy, invisible forces that govern the universe's structure and expansion, yet elude direct detection. Delving deeper, the universe's vastness is almost beyond comprehension, stretching over billions of light-years across. This immensity houses an estimated 2 trillion galaxies, each a collection of billions of stars and untold planets, offering a humbling perspective on our place in the cosmos. The laws of physics, consistent throughout the universe, govern the motion of galaxies, the life cycle of stars, and the intricate dance of particles at the quantum level. These laws have allowed scientists to predict cosmic phenomena with astonishing accuracy, from the paths of planets to the behavior of black holes, those enigmatic entities whose gravitational pull is so strong that not even light can escape. In this cosmic journey, the role of dark energy in accelerating the universe's expansion poses a tantalizing puzzle. Discovered through observations of distant supernovae, dark energy works against the gravitational pull of matter, driving galaxies apart at an accelerating rate. This discovery has profound implications for the fate of the universe, suggesting a future in which galaxies drift ever farther apart, leading to a cold, dilute cosmos. The Big Bang Theory stands as a cornerstone of modern cosmology, offering a compelling explanation for the origin and evolution of the universe. It posits that the universe began as an extremely hot and dense point approximately 13.8 billion years ago and has been expanding ever since. This theory is supported by a wealth of scientific evidence, including the observation of the cosmic microwave background radiation, a faint glow left over from the early universe, which provides a snapshot of the cosmos just 380,000 years after the Big Bang. This radiation, discovered accidentally by Arno Penzias and Robert Wilson in 1965, has a uniform temperature throughout the universe, confirming predictions of the Big Bang Theory and offering concrete evidence of the universe's hot, dense origin. Another pillar supporting the Big Bang Theory is the observation of the redshift of galaxies, indicating that they are moving away from us and, by implication, from each other. This discovery, made by Edwin Hubble in the 1920s, revealed that the universe is not static, but expanding. The farther away a galaxy is, the faster it appears to be moving away from us, a relationship now known as Hubble's law. This expansion is a key prediction of the Big Bang Theory and suggests that the universe was once much smaller, hotter, and denser than it is today. Moreover, the theory elegantly explains the relative abundances of light elements such as hydrogen, helium, and lithium observed in the universe. According to Big Bang nucleosynthesis, these elements were formed in the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to combine into nuclei. The predicted abundances of these elements closely match observations, lending further credence to the Big Bang Theory. Despite its widespread acceptance, the Big Bang theory also raises profound questions and puzzles. For instance, it does not explain what preceded the Big Bang or what lies outside the observable universe. It also introduces the concept of cosmic inflation, a rapid expansion of the universe that occurred fractions of a second after the Big Bang to solve the horizon and flatness problems. This inflationary period predicts that the universe should appear flat and uniform on large scales, which is consistent with observations of the cosmic microwave background radiation. Following the Big Bang, the universe embarked on a monumental journey of expansion, transforming from an infinitesimally small point to the vast cosmos we observe today. This expansion can be likened to a balloon being inflated, where galaxies move away from each other as the space between them grows. In the earliest moments, the universe was a hot, dense soup of particles and radiation, too energetic and chaotic for atoms to form. As it expanded, this primordial fireball cooled, allowing quarks to combine into protons and neutrons, which then formed the simplest nuclei, predominantly hydrogen and helium, through the process of nucleosynthesis. This phase of rapid expansion, occurring less than a trillionth of a second after the Big Bang, is theorized to have been driven by cosmic inflation. Cosmic inflation posits that the universe expanded at a rate much faster than the speed of light during this brief period. This exponential expansion smoothed out the distribution of energy and matter across the cosmos, laying the groundwork for the uniformity we observe in the cosmic microwave background radiation. It's a concept that challenges our everyday understanding of physics, suggesting that the rules of the cosmic scale can differ vastly from those governing our observable world. As the universe continued to expand and cool, gravity began to sculpt the distribution of matter, pulling particles together to form the first stars and galaxies. These celestial bodies acted as cosmic furnaces, forging heavier elements in their cores and releasing them into space when they died, seeding the cosmos with the building blocks for planets and life. The universe's expansion is not uniform. It's influenced by the distribution of matter and energy, leading to the formation of a web-like structure of galaxies and galaxy clusters interspersed with vast voids. This expansion is still ongoing, with galaxies moving away from us in all directions. The discovery that this expansion is accelerating was a groundbreaking revelation, hinting at the presence of dark energy, a mysterious force that permeates space and exerts a repulsive force, counteracting gravity. The exact nature of dark energy remains one of the most pressing mysteries in cosmology, with researchers striving to understand how it will influence the future evolution of the first second after the Big Bang presents a timeline of incredible transformations that laid down the fundamental structure of our universe. Imagine the universe at its inception, an unimaginably hot and dense point. Within a fraction of the first second, the universe began expanding rapidly in an event known as inflation, stretching far beyond the realms of our current comprehension, setting the stage for everything that would follow. This initial expansion was so rapid that it took less than a blink of an eye for the universe to grow from smaller than an atom to a size larger than a galaxy. As it expanded, the temperature began to fall, allowing the fundamental forces of nature to start separating from each other. During the first tiny fraction of a second, gravity separated from the grand unified force, marking the first major transition in the early universe. Following this, as the universe cooled further, the strong nuclear force, responsible for holding the nucleus of an atom together, separated from the electroweak force, which is a combination of the electromagnetic force and the weak nuclear force. This separation marked the universe's transition from a state where all forces were unified to a state where the distinct forces we observe today began to emerge. Within the first second, the universe cooled enough for quarks, the building blocks of protons and neutrons, to start combining. These quarks initially existed in a free state due to the extreme temperatures, but as the universe expanded and cooled, they began to bind together, forming protons and neutrons. This process, known as baryogenesis, was crucial for the formation of matter as we know it. Simultaneously, the universe was filled with a dense, hot plasma of quarks, electrons, and neutrinos. As it continued to expand and cool, interactions between these particles started to change. For instance, as the universe cooled further, quarks combined into protons and neutrons, and eventually these protons and neutrons would form the nuclei of the first elements. The end of the first second marked a universe that, while still incredibly hot and dense by any standard we're familiar with today, had cooled sufficiently for the basic forces of nature to have taken their present forms, and for the first building blocks of matter to solidify into existence. The stage was set for the next phase of cosmic evolution, leading towards the formation of atoms, stars, galaxies, and eventually the complex structures we observe in the universe today. This rapid sequence of events in the first second after the Big Bang illustrates not just the dynamic nature of our universe's birth, but also the intricate interplay of forces and particles that underpin the fabric of everything we know. Quarks are the very essence of the matter that makes up the world around us, yet they remain shrouded in the mysteries of quantum physics, a field that fascinates and perplexes even the most seasoned scientists. To grasp the concept of quarks, imagine them as the fundamental building blocks of matter, smaller than atoms, protons, or neutrons, and playing a crucial role in the composition of the universe. These particles are so minuscule and elusive that they cannot exist independently in nature. They are always found in groups, binding together to form larger particles like protons and neutrons, which in turn make up the nucleus of an atom. The story of how quarks formed takes us back to the very beginning of the universe, in the immediate aftermath of the Big Bang, during a period known as the Quark Epoch. This epoch occurred within the first microsecond, 1/1,000,000th of a second, after the Big Bang, a time when the universe was so hot and dense that particles as we know them could not yet exist. The temperatures were so extreme, reaching trillions of degrees, that matter existed in a state known as a quark-gluon plasma. In this plasma, quarks, along with gluons, which act as the exchange particles or glue holding quarks together, moved freely in a soup of primordial energy. As the universe expanded, it cooled at a rapid pace, allowing quarks to finally combine to form protons and neutrons. This process required the universe to cool to a point where the strong nuclear force, one of the four fundamental forces of nature, could take effect. The strong force is incredibly powerful, but operates over very short distances, and it was this force that glued quarks together in combinations of 2 or 3 to form composite particles, such as mesons, made of 1 quark and 1 antiquark, and baryons, made of 3 quarks, respectively. Protons and neutrons are the most stable and familiar types of baryons, essential components of atomic nuclei. Following the journey from quarks to the more familiar protons and neutrons that form the nucleus of an atom, we delve into a fascinating process that unfolded in the universe's infancy. After the Big Bang, as the universe expanded and cooled, conditions became ripe for the binding of quarks, leading to the formation of protons and neutrons, a crucial step in the cosmic recipe that would eventually give rise to atoms, stars, planets, and life itself. During the Quark Epoch, the universe was a hot, dense soup of quarks and gluons. Quarks are the fundamental constituents of matter, coming in 6 flavors: up, down, charm, strange, top, and bottom. For protons and neutrons, only up and down quarks are directly involved. Gluons are the carriers of the strong force, acting as a powerful glue that holds quarks together, despite their tendency to repel each other due to their charges. As the universe cooled down from its initial fiery state, it crossed a threshold temperature that allowed quarks to start combining, a momentous event occurring approximately 1 microsecond after the Big Bang. This cooling period allowed the strong nuclear force, one of the 4 fundamental forces of nature, to dominate over the thermal kinetic energy that kept quarks apart. When this happened, quarks began to stick together in stable groups known as hadrons. Protons and neutrons are types of hadrons. A proton is made of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The specific combination of quarks determines the properties of the particle, such as its charge. Protons are positively charged, and neutrons are neutral. This distinction plays a vital role in how atoms and molecules, the building blocks of matter, are formed and interact. The formation of protons and neutrons from quarks was a critical step in the early universe's evolution. It marked the beginning of the end for the quark-gluon plasma state and the start of a universe filled with matter as we know it. Once protons and neutrons formed, they could begin to come together, forming the nuclei of the simplest elements, a process known as nucleosynthesis. This sequence of events set the stage for the chemical complexity necessary for the stars, galaxies, and life to eventually emerge. As we continue to unravel the universe's early moments, the role of the fundamental forces becomes a pivotal chapter in the cosmic saga. These forces, which are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, acted as the architects of the universe, sculpting the raw materials created in the aftermath of the Big Bang into the complex structures we observe today. In the universe's first moments, all forces were unified into a single force. As the universe expanded and cooled, this unified force began to break apart in a process known as symmetry breaking. The first to separate was gravity, which plays a crucial role in shaping the large-scale structure of the universe by influencing the motion of galaxies and clusters of galaxies. Despite being the weakest of the 4 forces, gravity's influence grows with the mass and distance, making it the dominant force on a cosmic scale. Following gravity, the strong nuclear force separated. This force is responsible for holding the nuclei of atoms together, overcoming the repulsive electromagnetic force between the positively charged protons. It was during this separation that quarks began to combine into protons and neutrons, as we've previously explored. The strong force ensured that these particles could form stable nuclei, setting the stage for the creation of the first atoms. The weak nuclear force and electromagnetism were the next to differentiate as the universe continued to cool. The weak force is key in the process of nuclear fusion and radioactive decay, playing a vital role in the life cycles of stars and the synthesis of elements heavier than hydrogen. Electromagnetism, on the other hand, governs the interactions between charged particles. It's the force behind the light, electricity, and magnetism, shaping the behavior of atoms and molecules, and thus the chemistry that underpins all of life. Together, these forces dictated the universe's evolution from a homogeneous soup of particles to a structured, diverse cosmos filled with galaxies, stars, planets, and ultimately life. They determined the formation of the first hydrogen and helium atoms in a process known as recombination, leading to the universe's transparency to light and the release of the cosmic microwave background radiation, a relic from this era that provides us with a snapshot of the infant universe. The interplay between these forces also drove the formation of stars and galaxies. Gravity pulled matter together, while electromagnetism and the nuclear forces governed the internal processes of stars, including nuclear fusion, which powers stars and generates the heavier elements essential for planets and life. Delving deeper into the mysteries of the universe, we pivot our attention towards the formation of the very first atoms, a seminal event that marked a turning point in the cosmic narrative. This process, known as recombination, occurred approximately 378,000 years after the Big Bang. Before this epoch, the universe was a hot, dense plasma of electrons, protons, and photons. The temperatures were so extreme that atoms could not form without being immediately torn apart by the rampant energy. As the universe expanded, it cooled down, allowing for the first atoms to emerge. Hydrogen, the simplest and most abundant element in the universe, was the first to form. This element, consisting of just one proton and one electron, marked the dawn of a new era in cosmic history. Helium atoms, slightly more complex with 2 protons, 2 neutrons, and 2 electrons, followed shortly after. These elements laid the foundation for the chemical diversity we observe in the universe today. The formation of these first atoms was a turning point that significantly altered the universe's structure and future evolution. With atoms now stable, they began to gravitate towards each other, slowly building the first stars and galaxies. This era set the stage for the complex chemical processes that would eventually lead to the formation of planets and life itself. Following the monumental formation of the first atoms in the universe, an equally remarkable phenomenon unfolded: the birth of the first molecules. This transition from solitary atoms to the earliest molecules marks a significant chapter in cosmic history, laying the groundwork for the complex chemistry that underpins the universe as we know it. The story of how the first molecules came into existence is not only a testament to the intricacies of the cosmos, but also to the relentless pursuit of knowledge that drives our understanding of it. As the universe continued to expand and cool, conditions gradually became favorable for these freshly formed atoms, primarily hydrogen and helium, to interact in novel ways. Hydrogen, with its single electron, was particularly predisposed to forming bonds with other hydrogen atoms. The emergence of molecular hydrogen, or H2, was a critical step forward. This molecule, though simple in structure, played a pivotal role in the universe's early chemistry. The formation of molecular hydrogen provided the first building blocks for more complex chemical reactions. It acted as a coolant, allowing gas clouds to collapse more efficiently under gravity, which in turn led to the formation of the first stars. These nascent stars were the crucibles in which the first heavy elements were forged, elements that would eventually give rise to the rich chemical tapestry that makes up planets, asteroids, comets, and all living organisms. The exact timing of the first molecule's formation is a subject of ongoing research, but it is believed to have occurred a few 100,000 years after the Big Bang, following closely on the heels of atomic formation. This era set the stage for the intricate interplay of forces that would eventually lead to the universe's structure, from galaxies to planets and the very essence of life itself. As we trace the cosmic lineage back to its origins, the roles of helium and hydrogen emerge as foundational to the early universe's evolution. These two elements, the simplest and most abundant in the cosmos, were instrumental in shaping the universe from its nascent stages. Their significance cannot be overstated, as they were the primary constituents of the primordial universe, setting the stage for all subsequent astronomical phenomena and the complex chemistry that characterizes the cosmos today. In the aftermath of the Big Bang, the universe was predominantly filled with hydrogen and helium. Hydrogen, being the lightest element with just one proton and one electron, formed the bulk of the matter in the early universe. Helium, slightly heavier with 2 protons and 2 electrons, was the second most abundant element. These elements were crucial for several reasons. First, their simplicity made them the building blocks for all other elements and molecules that would later emerge through nuclear processes within stars. The significance of hydrogen extends beyond its abundance. It played a central role in the formation of the first stars, known as population 3 stars. These stars were massive, hot, and short-lived, but they were critical for the synthesis of heavier elements through nuclear fusion. As these first stars ended their lives in spectacular supernovae, they seeded the cosmos with heavier elements, which would eventually give rise to new stars, planets, and, ultimately, life as we know it. Helium's role, while less directly involved in chemical complexity, was no less important. Its presence influenced the dynamics of stellar evolution. Stars fuse hydrogen into helium in their cores, a process that releases vast amounts of energy and light. As stars age, they begin to fuse helium into heavier elements, leading to different types of stellar outcomes and contributing to the diversity of astronomical objects we observe today. Moreover, the ratio of hydrogen to helium in the universe provides critical insights into the conditions of the early universe and supports the Big Bang theory. Observations of this primordial helium abundance, along with the cosmic microwave background radiation, offer compelling evidence of the universe's hot, dense beginnings. Building on our journey through the cosmos, where we've uncovered the roles of helium and hydrogen, we arrive at another cornerstone of cosmology, the cosmic microwave background, CMB, radiation. This phenomenon is essentially the afterglow of the Big Bang, the ancient light that bathes the universe, providing us with a snapshot of the infant cosmos. CMB radiation is a pivotal piece of evidence for the Big Bang theory, offering a window back in time to when the universe was just about 380,000 years old. At this juncture in cosmic history, the universe had cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms, a process known as recombination. Prior to this, the universe was a plasma of charged particles and photons, light particles, which scattered off each other frequently. However, as the universe expanded and cooled, photons could travel freely without being scattered, leading to the universe becoming transparent. The CMB is the relic of this transition, stretched to microwave wavelengths by the expansion of the universe over billions of years. The significance of the CMB radiation lies not only in its confirmation of the Big Bang theory, but also in the detailed information it provides about the early universe's conditions. The tiny temperature fluctuations within the CMB are particularly revealing. These minute differences in density and temperature are thought to be the seeds from which all the current structures in the universe, such as galaxies and clusters of galaxies, have grown. Measurements of the CMB radiation have led to precise determinations of various fundamental parameters of the universe, including its age, composition, and the rate of its expansion. For instance, the CMB data suggest that the universe is approximately 13.8 billion years old and composed of about 5% ordinary matter, 25% dark matter, and 70% dark energy. Venturing further into the cosmic narrative, we explore how the CMB radiation underpins the Big Bang theory, a pivotal concept in cosmology. The Big Bang theory proposes that the universe originated from an extremely hot and dense state and has been expanding ever since. The CMB radiation is a critical piece of evidence supporting this theory, offering tangible insights into the universe's early moments. The discovery of the CMB radiation in the mid-20th century was a landmark event that provided the first direct observational evidence of the universe's hot, dense beginnings. The CMB's uniformity, with its temperature incredibly uniform across the sky at about 2.7 Kelvin, minus 270.45 degrees Celsius, yet punctuated by tiny fluctuations, paints a picture of the early universe's state. These tiny temperature variations are crucial. They indicate regions of slightly different densities, representing the seeds of all current cosmic structures, from galaxies to clusters of galaxies. The Big Bang theory predicts that after the initial explosion, the universe was in a state of extreme heat and density, filled with a primordial soup of particles and radiation. As the universe expanded, it cooled, leading to the formation of neutral atoms, which allowed photons to travel freely. The CMB radiation is the relic of this epoch, stretched to microwave wavelengths by the universe's expansion, and observed today as the cosmic afterglow of that monumental event. Furthermore, the detailed analysis of the CMB's temperature fluctuations through experiments like the COBE Cosmic Background Explorer, WMAP Wilkinson Microwave Anisotropy Probe, and Planck satellite missions has provided precise measurements of the universe's age, composition, and rate of expansion. These observations match remarkably well with predictions from the Big Bang theory, reinforcing its validity. For instance, the slight anisotropies, irregularities, in the CMB reveal the distribution of matter and energy in the early universe, which, according to the Big Bang theory, should be relatively uniform, but with minor variations that led to the formation of galaxies and larger structures. The CMB's existence and its properties are thus in strong agreement with the theoretical predictions of the Big Bang, providing compelling evidence that our universe did indeed begin from a hot, dense state and has been expanding over time. Delving into the CMB radiation has opened up new vistas in our understanding of the universe. This relic radiation, a faint cosmic afterglow from the Big Bang, serves as a cosmic treasure trove, revealing details about the universe's infancy and its subsequent evolution. By studying the CMB, scientists have gleaned invaluable insights that have significantly advanced our comprehension of cosmology. One of the most profound learnings from the CMB is the confirmation of the universe's age. Precise measurements of the CMB's fluctuations have enabled scientists to estimate that the universe is approximately 13.8 billion years old. This provides a concrete timeline for the universe's history, from its fiery origins to the present day, grounding our understanding of cosmic evolution in empirical evidence. The composition of the universe is another area where the CMB has provided critical information. Analysis of the CMB data has helped scientists determine the universe's makeup. Roughly 5% ordinary matter, the matter that makes up stars, planets, and living beings, 25% dark matter, a mysterious substance that exerts gravitational pull but does not emit light, and 70% dark energy, a mysterious force that is causing the universe's expansion to accelerate. These proportions have profound implications for our understanding of the universe, highlighting the dominance of dark matter and dark energy in cosmic dynamics. The CMB has shed light on the geometry of the universe. The size and distribution of the temperature fluctuations within the CMB suggest that the universe is flat with a margin of error. This flatness implies that the geometry of the universe is such that parallel lines will never converge or diverge, influencing the universe's overall shape and expansion. The study of the CMB has also contributed to our understanding of the inflationary theory, which posits that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The uniformity and structure of the CMB across the vast expanse of the sky support the idea that the universe expanded exponentially during its earliest moments, smoothing out any initial irregularities and leading to the uniform universe we observe today, albeit with slight variations that gave rise to galaxies and other structures. The CMB has acted as a backdrop for exploring the potential for new physics beyond the Standard Model. Anomalies and unexplained aspects of the CMB, such as the cold spot or slight discrepancies in temperature fluctuations, invite ongoing research and theories that may extend our current understanding of physics. As the afterglow of the Big Bang began to fade, the universe entered a period known as the Cosmic Dark Ages, a time that lasted for about 380,000 years to 1 billion years after the universe's inception. During this era, the universe was filled with a dense, cooling fog of hydrogen gas, rendering it opaque and, in a sense, invisible to the kind of light we can now observe with telescopes. Without stars or galaxies to illuminate it, this epoch stands as an enigmatic chapter in cosmic history, a stretch of time when the cosmos was eerily silent and dark. The cosmic dark ages are a critical period in the universe's evolution, laying the groundwork for the formation of the first stars and galaxies. As the universe expanded, the primordial gas that filled it began to clump together under the influence of gravity. These regions of higher density eventually became the nurseries for the first stars, known as Population 3 stars. Unlike the stars we see today, these celestial bodies were massive, luminous, and short-lived, composed almost entirely of hydrogen and helium. The nuclear reactions within these stars eventually ionized the surrounding hydrogen gas, piercing the opaque veil of the cosmic dark ages and bringing the universe into a new era of transparency and light. This transition, known as cosmic reionization, marked the end of the cosmic dark ages and set the stage for the rich tapestry of structures we observe in the universe today. The light from these first stars and galaxies began to travel through the cosmos, gradually illuminating the once dark universe. This period is of intense interest to astronomers and cosmologists, as it holds clues to the formation of the first cosmic structures and the nature of dark matter, a mysterious substance that exerts a gravitational pull, yet does not emit, absorb, or reflect light. Studying the cosmic dark ages poses significant challenges, as the light from this period is exceedingly faint and difficult to detect. However, with advancements in technology and the advent of next-generation telescopes, scientists are beginning to pierce this veil. Observations of distant quasars and galaxies, along with the cosmic microwave background radiation, a relic from the Big Bang, provide valuable insights into this pivotal era. These studies not only shed light on the dark ages themselves, but also help us understand the fundamental processes that have shaped the universe from its earliest moments to the present day. Emerging from the cosmic dark ages, the universe embarked on a transformative journey, culminating in the birth of the first stars and galaxies. This pivotal epoch, occurring roughly around 100 million years after the Big Bang, signifies a monumental shift in the cosmic narrative. Initially, the universe was a homogeneous soup of hydrogen and helium gas. However, subtle fluctuations in density, possibly amplified by the mysterious dark matter that pervades the cosmos, began to create pockets where the gas was slightly more concentrated. Gravity, the architect of cosmic evolution, took hold within these denser regions, pulling the gas inward. As these clouds of gas grew denser and hotter, they reached a critical threshold, igniting the nuclear fusion processes at their cores. This marked the birth of the first stars, colossal and bright, primarily composed of hydrogen and helium. These Population 3 stars were giants compared to their modern counterparts, burning with such intensity that their lifespans were relatively brief on a cosmic scale. The ignition of the first stars introduced light back into the universe, ending the cosmic dark ages. These stars were not solitary beacons. They began to clump together under gravity's relentless pull, forming the nuclei of the first galaxies. These early galaxies were smaller and less structured than the ones we see today. Yet they were the seeds from which the grand spirals and vast ellipticals of the current universe would grow. As these first stars aged, they played a crucial role in the chemical enrichment of the cosmos. The nuclear fusion processes at their hearts forged heavier elements like carbon, oxygen, and iron, elements that had not existed before. When these stars reached the end of their lives, they expelled these heavier elements into space through supernova explosions, seeding the cosmos with the building blocks necessary for future generations of stars, planets, and eventually life. The formation of the first stars and galaxies set in motion a complex web of interactions that would shape the universe's evolution. The radiation from the first stars helped to reionize the surrounding medium, clearing the fog of the early universe and making it transparent to light. This process, known as cosmic reionization, was a gradual one, stretching from about 150 million to a billion years after the Big Bang, and was essential for the universe to become the starlit expanse we observe today. As the first stars and galaxies began to illuminate the cosmos, an invisible scaffold was already in place, guiding their formation and distribution across the universe. This unseen framework is known as dark matter, a term that encompasses a vast portion of the universe's total mass. Unlike the stars, planets, and gas clouds that emit or reflect light, dark matter does not interact with electromagnetic forces, making it completely invisible to our current observational instruments. Despite its elusive nature, dark matter plays a crucial role in the cosmos, especially in the formation of large-scale structures like galaxies and galaxy clusters. The existence of dark matter was first inferred from the gravitational effects it has on visible matter. For instance, galaxies spin at such speeds that, without the presence of a significant amount of unseen mass, they would simply fly apart. Furthermore, the way galaxies cluster together, along with observations of the cosmic microwave background radiation, the afterglow of the Big Bang, suggests that there is far more matter in the universe than we can directly observe. Studies estimate that dark matter constitutes about 85% of the total matter in the universe, a figure that underscores its importance in cosmic evolution. Dark matter played a pivotal role in the formation of cosmic structures. In the early universe, slight density fluctuations became the seeds for the first structures to form. Dark matter, unaffected by anything but gravity, began to clump together in these denser regions, forming vast halos that would serve as gravitational wells, pulling in the normal or baryonic matter. This process accelerated the formation of stars and galaxies, as hydrogen and helium gas fell into the gravitational pits carved out by dark matter. These dark matter halos provided the necessary gravitational framework for the gas to cool and condense into stars. As these stars formed and grouped into the first galaxies, they followed the underlying dark matter distribution, leading to the large-scale structure of the universe we see today, with galaxies and galaxy clusters woven into a cosmic web of filaments and voids. This structure, predicted by simulations that include dark matter, matches observations of the universe at large scales remarkably well. The role of dark matter in cosmic structure formation is a topic of ongoing research and fascination in cosmology. Its presence is inferred from its gravitational effects, yet its true nature remains one of the biggest mysteries in science. Various candidates have been proposed for what dark matter might be, ranging from exotic particles like WIMPs, weakly interacting massive particles, to axions, particles much lighter than electrons. Despite extensive searches, direct detection of dark matter particles has yet to be achieved, making its study a frontier of both theoretical and experimental physics. Following the threads woven by dark matter in the cosmic tapestry, we find that the formation of stars from cosmic gas is a natural progression in the story of the universe. Stars begin their lives within vast, cold clouds of gas and dust, known as molecular clouds or nebulae. These clouds are mostly composed of hydrogen, with a sprinkling of helium and trace amounts of heavier elements. Within these nebulae, regions of higher density can form, often triggered by the gravitational influence of dark matter, as well as by the effects of nearby supernova explosions or the collision of gas clouds. When these denser regions reach a critical mass, gravity begins to overpower the internal pressures resisting collapse. The cloud starts to contract, and as it does, the material at the center of the cloud becomes increasingly dense and hot. This process can take millions of years, but it's the crucial first step towards star formation. During this phase, the collapsing material forms what is known as a protostar, a hot core that is the precursor to a star. As the protostar continues to accumulate mass from its surrounding cloud, its temperature rises. When the core's temperature reaches about 10 million degrees Celsius, nuclear fusion ignites. This process involves hydrogen nuclei fusing to form helium, releasing a tremendous amount of energy in the process. This energy generation marks the birth of a new star. The onset of nuclear fusion halts the gravitational collapse, establishing a stable balance between the inward pull of gravity and the outward push of the energy produced by fusion. This delicate balance is what sustains a star throughout most of its life. The size and mass of the resulting star depend on how much material from the surrounding cloud it can gather before nuclear fusion begins. More massive stars form from denser or more extensive clouds and have shorter lifespans because they burn through their nuclear fuel more quickly. In contrast, smaller stars like our Sun have longer lifespans, burning their fuel more slowly and steadily. Stars do not form in isolation. Within a single molecular cloud, many stars can form simultaneously, creating a cluster of newborn stars. This communal birth often results in stellar associations and open clusters, where stars remain gravitationally bound to each other for some time before dispersing. The process of star formation from cosmic gas is not only a testament to the dynamic nature of the universe, but also to the interconnectedness of all cosmic phenomena. Each star's birth contributes to the chemical richness of the cosmos, seeding the universe with elements critical for the formation of planets and potentially life itself. The life cycle of a star is a fascinating journey that spans millions to billions of years, showcasing the dynamic processes that drive the evolution of the cosmos. This cycle begins in the dense, cold cores of molecular clouds, where stars are born from collapsing pockets of gas and dust. As we've seen, the gravitational pull within these regions leads to the formation of protostars, which eventually ignite into full-fledged stars once nuclear fusion starts in their cores. The path a star takes through its lifetime depends largely on its initial mass. Smaller stars, like our Sun, enter what is known as the main sequence phase after their birth. During this stage, which constitutes the majority of a star's life, hydrogen fusion occurs in the core, producing helium and releasing energy that supports the star against gravitational collapse. For a star like the Sun, the main sequence phase can last about 10 billion years. As stars exhaust their hydrogen fuel, their lives continue to evolve dramatically. In the case of a Sun-like star, once the hydrogen in the core is depleted, fusion ceases. The life cycle of a star is not just a sequence of events. It's a cornerstone of cosmic evolution, contributing to the chemical complexity of the universe and influencing the formation and evolution of galaxies. Within the crucibles of stars, a process unfolds that has puzzled and fascinated scientists for generations: the creation of heavier elements from lighter ones. This alchemical process, known as nuclear synthesis, is the heart of a star's contribution to the cosmos. It begins with the fusion of hydrogen, the most abundant element in the universe, into helium, the second lightest element. This process releases energy, which provides the light and heat we associate with stars, including our Sun. But the story doesn't end there. As stars evolve, particularly those more massive than the Sun, their internal conditions become extreme enough to fuse helium and other lighter elements into heavier ones. In the cores of these stars, temperatures and pressures reach staggering levels, enabling a series of nuclear fusion reactions that form elements such as carbon, oxygen, silicon, and iron. Each step up the ladder of complexity requires increasingly harsh conditions, only found in the cores of the largest stars or in the explosive environments of supernovae. For instance, carbon is formed from the fusion of 3 helium nuclei, a process requiring temperatures exceeding 100 million degrees Celsius. The journey from lighter to heavier elements culminates with iron, the most stable of all nuclear matter. Here, the process of fusion reaches a critical threshold. Unlike lighter elements, fusing iron does not release energy, it consumes it. Thus, when a star's core is converted to iron, it marks the beginning of the end of the star's life. Without the energy released from fusion to counteract gravity, the core collapses, leading to a supernova explosion for the most massive stars. It is in the cataclysmic violence of these supernovae that the heaviest elements of all, such as gold, uranium, and plutonium, are created. The remnants of these explosions, enriched with a cornucopia of elements, are then cast into the cosmos, seeding future generations of stars and planets. This cosmic recycling process ensures that the elements necessary for life are not confined to the interiors of distant stars, but are instead spread throughout the universe. The iron in our blood, the calcium in our bones, and the oxygen we breathe are all forged in the fiery hearts of stars long gone, a testament to the profound connection between the cosmos and every living thing within it. When stars reach the end of their lives, the universe stages a dramatic farewell, showcasing a variety of cosmic phenomena that depend on the mass of the dying star. The death of a star marks not just an end, but also the beginning of a new chapter in the cosmic cycle of matter. For stars like our Sun, the final act begins when all the hydrogen in the core has been fused into helium and the star expands into a red giant. This expansion is the star's attempt to find a new equilibrium as it starts fusing helium into heavier elements like carbon and oxygen in its core or in shells around the core. Eventually, the star sheds its outer layers into space, creating a visually stunning planetary nebula, leaving behind a hot core that cools and dims over time, becoming a white dwarf. This dense, Earth-sized remnant will spend billions of years cooling and fading into the cosmic backdrop, its nuclear fires extinguished. The fate of more massive stars is far more violent and spectacular. When these stars exhaust their nuclear fuel, they undergo a series of increasingly rapid and energetic fusion reactions, creating a layered structure of elements with iron at the core. Since iron cannot produce energy through fusion, the star no longer has a source of pressure to counteract gravity, leading to a catastrophic collapse of the core in a matter of seconds. This collapse triggers a supernova explosion, one of the most energetic events in the universe, briefly outshining entire galaxies and dispersing the elements forged within the star into space. The remnants of this explosion can lead to the formation of either a neutron star, an incredibly dense object only about 20 kilometers in diameter, but with more mass than the Sun, or if the star was massive enough, a black hole, a point in space where gravity is so strong that not even light can escape. These end-of-life events are not just spectacular cosmic fireworks. They play a crucial role in the evolution of the universe. The elements produced and dispersed by dying stars seed the cosmos with the materials necessary for new stars, planets, and potentially life itself to form. Supernovae, in particular, are responsible for creating and distributing the heavy elements essential to our existence. Delving into the cosmic ballet of galaxy formation, we embark on a journey that spans billions of years, where the universe's fundamental forces choreograph the creation of these colossal celestial entities. Galaxies, Vast islands of stars, gas, dust, and dark matter are the building blocks of the cosmos, and their formation is a tale of both simplicity and complexity, woven by the laws of physics. In the beginning, following the Big Bang, the universe was a hot, dense sea of particles. As it expanded, temperatures dropped, allowing protons and electrons to combine and form neutral hydrogen atoms. This era, known as recombination, marked the universe's transition from opacity to transparency, allowing light to travel freely for the first time. However, the universe was not perfectly uniform. Slight density variations, or ripples in the fabric of space-time, left by the Big Bang, set the stage for galaxy formation. Gravity, the architect of the cosmos, took center stage, amplifying these tiny fluctuations. Regions slightly denser than their surroundings began to attract more and more matter, growing increasingly more massive. This process is beautifully illustrated by the concept of gravitational collapse, where gas clouds, primarily hydrogen, begin to collapse under their own gravity. As these clouds condensed, they formed the first stars and proto-galaxies, simple structures that would evolve into the complex galaxies we observe today. However, galaxy formation is not solely a product of gravity's inward pull. Other forces played pivotal roles, such as dark matter, a mysterious substance that does not emit, absorb, or reflect light, but exerts gravitational effects on visible matter. Dark matter makes up about 85% of the universe's total matter content and acted as scaffolding for galaxy formation. It clumped together in the early universe, creating gravitational wells into which ordinary matter could fall, accelerating the process of galaxy assembly. Moreover, feedback processes, where energy from star formation and supernova explosions heated and expelled gas from early galaxies, also significantly influenced their evolution. These energetic outflows prevented the gas from cooling and collapsing too quickly, regulating the pace of star formation and leading to the diverse array of galaxy sizes and shapes observed today, from spiral galaxies like our Milky Way to elliptical and irregular galaxies. As galaxies grew, they did not evolve in isolation. Collisions and mergers between galaxies were common, especially in the crowded environment of the early universe. These cosmic encounters could dramatically alter a galaxy's structure and star formation rate, creating new morphological features such as spiral arms and seeding the growth of supermassive black holes at their centers. Today, galaxies continue to evolve, influenced by their interactions with their environment, including other galaxies and intergalactic gas. The study of galaxy formation and evolution not only sheds light on the history of the universe, but also provides crucial insights into the fundamental processes governing the cosmos. It's a narrative of creation, transformation, and interaction, highlighting the intricate dance of matter and energy that shapes our universe. In the vast expanse of the universe, galaxies are the grand assemblies of stars, gas, dust, and dark matter, presenting themselves in a variety of magnificent forms. These cosmic entities, numbering in the billions, are classified into several main types, each with its own unique characteristics and origins, painting a rich tapestry of the cosmos's diversity. Among these types, spiral, elliptical, and irregular galaxies stand out, each telling a different story of cosmic evolution and interaction. Spiral galaxies, such as our Milky Way, are distinguished by their flat, disc-like appearance featuring swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars, around which the arms, sites of active star formation, wrap themselves in graceful arcs. These arms are rich in gas and dust, the raw materials for new stars, and are often highlighted by bright nebulae and young, hot stars that give them a distinct glow. The spiral pattern is thought to be a result of density waves that sweep through the galaxy, compressing gas and dust to spark star formation in a ripple effect. Elliptical galaxies, in contrast, lack the defined structure and spiral arms of their disc-shaped counterparts. They range from nearly spherical to elongated shapes and are composed mostly of older, redder stars with minimal gas and dust. This makes them relatively barren in terms of new star formation. The size of elliptical galaxies can vary widely, from giants that dominate their local clusters of galaxies to dwarfs that flit like shadows around their larger neighbors. The formation of these galaxies is often attributed to the merging of smaller galaxies, a process that strips away gas and leaves behind a smoother, less structured formation. Irregular galaxies, as the name suggests, lack the coherent structure seen in spiral and elliptical galaxies. These galaxies are often chaotic in appearance, without a defined form, and are rich in gas and dust, making them fertile grounds for star formation. Their irregular shapes can be the result of gravitational interactions or collisions with other galaxies, which distort their structure and trigger bursts of star formation. These galaxies are important to astronomers as they often provide insights into the processes of galaxy interaction and evolution. Beyond these broad categories, there are also subtypes and peculiar galaxies that defy easy classification, often resulting from the dynamic and sometimes violent interactions between galaxies. For example, lenticular galaxies possess a large central bulge and a disk, but lack the spiral arms, sitting in a category between spiral and elliptical galaxies. This diversity underscores the complexity of cosmic evolution and the influence of gravity, collision, and merger events in shaping the universe's structure. In the vast expanse of the universe, galaxies are the grand assemblies of stars, gas, dust, and dark matter, presenting themselves in a variety of magnificent forms. These cosmic entities, numbering in the billions, are classified into several main types, each with its own unique characteristics and origins, painting a rich tapestry of the cosmos's diversity. Among these types, spiral, elliptical, and irregular galaxies stand out, each telling a different story of cosmic evolution and interaction. Spiral galaxies, such as our Milky Way, are distinguished by their flat, disc-like appearance, featuring swirling arms that emanate from a central bulge. This bulge is a dense concentration of older stars, around which the arms, sites of active star formation, wrap themselves in graceful arcs. These arms are rich in gas and dust, the raw materials for new stars, and are often highlighted by bright nebulae and young hot stars that give them a distinct glow. The spiral pattern is thought to be a result of density waves that sweep through the galaxy, compressing gas and dust to spark star formation in a ripple effect. Elliptical galaxies, in contrast, lack the defined structure and spiral arms of their disc-shaped counterparts. They range from nearly spherical to elongated shapes and are composed mostly of older, redder stars with minimal gas and dust. This makes them relatively barren in terms of new star formation. The size of elliptical galaxies can vary widely, from giants that dominate their local clusters of galaxies to dwarfs that flit like shadows around their larger neighbors. The formation of these galaxies is often attributed to the merging of smaller galaxies, a process that strips away gas and leaves behind a smoother, less structured formation. Irregular galaxies, as the name suggests, lack the coherent structure seen in spiral and elliptical galaxies. These galaxies are often chaotic in appearance, without a defined form, and are rich in gas and dust, making them fertile grounds for star formation. Their irregular shapes can be the result of gravitational interactions or collisions with other galaxies, which distort their structure and trigger bursts of star formation. These galaxies are important to astronomers as they often provide insights into the processes of galaxy interaction and evolution. Beyond these broad categories, there are also subtypes and peculiar galaxies that defy easy classification, often resulting from the dynamic and sometimes violent interactions between galaxies. For example, lenticular galaxies possess a large central bulge and a disk, but lack the spiral arms, sitting in a category between spiral and elliptical galaxies. This diversity underscores the complexity of cosmic evolution and the influence of gravity, collision, and merger events in shaping the universe's structure. The story of the Milky Way's formation is a cosmic saga that spans billions of years, weaving together the forces of gravity, the mysteries of dark matter, and the life cycle of stars. At the heart of this narrative is the concept of hierarchical assembly, a process by which smaller components merge to form larger structures, a principle that underpins the evolution of galaxies across the universe. Our Milky Way, a barred spiral galaxy with vast swirling arms wrapped around a luminous core, began its life about 13.6 billion years ago, not long after the Big Bang. In the early universe, a period marked by a cosmic soup of hydrogen, helium, and traces of lithium, slight irregularities in density, perhaps influenced by the enigmatic nature of dark matter, began to coalesce under the relentless pull of gravity. These denser regions attracted more matter, growing into the first protogalaxies, the building blocks of modern galaxies. As these protogalaxies orbited each other, their mutual gravitational attractions pulled them closer, leading to a series of mergers. With each merger, the nascent Milky Way grew in size and complexity. Dark matter, invisible yet detectable through its gravitational influence, played a pivotal role in this process, guiding the assembly of gas and stars into the fledgling galaxy's growing structure. The formation of the Milky Way's disk, where our solar system resides, is a testament to the gradual yet dynamic nature of galactic evolution. Over billions of years, gas settling into the galactic plane spiraled inward, conserving angular momentum, and began forming new stars. This process enriched the galaxy's composition, as successive generations of stars synthesized heavier elements in their cores and seeded the galaxy with the materials necessary for planets and life. Central to the Milky Way is the bulge, a dense concentration of stars, including many of the galaxy's oldest, which formed in the early stages of its history. Surrounding the bulge and disk is the halo, a more diffuse region populated with globular clusters, spherical collections of stars bound together by gravity, and the remnants of smaller galaxies that were consumed by the Milky Way. The Milky Way's spiral arms, sites of active star formation, trace their origins to density waves that ripple through the galaxy's disk. These waves compress gas and dust, triggering the birth of new stars, which in turn illuminate the arms, making them visible across cosmic distances. Throughout its history, the Milky Way has continued to grow and evolve through the accretion of gas and the merger with other galaxies. One of the most significant upcoming events in its life story is the predicted collision with the Andromeda Galaxy, our nearest spiral galaxy neighbor, expected to occur in about 4 billion years. This event will mark the next chapter in the Milky Way's evolution, transforming it and Andromeda into a new, larger galaxy. In the cosmic mix of galaxies, supermassive black holes occupy a pivotal role, acting as both anchors and architects that shape the evolution of galaxies. Nestled at the heart of nearly every large galaxy, including our own Milky Way, these gravitational behemoths, with masses ranging from millions to billions of times that of our Sun, exert a profound influence on their cosmic surroundings. The relationship between supermassive black holes and their host galaxies is one of the most fascinating topics in modern astrophysics, highlighting a complex interplay between the seemingly insatiable gravity of black holes and the vast ecosystems of stars, gas, and dust that comprise galaxies. One of the key insights into this relationship is the discovery of a correlation between the mass of a galaxy's central black hole and various properties of the galaxy's bulge, such as mass and velocity dispersion. This correlation suggests a deep intrinsic link between the growth of supermassive black holes and the evolution of galaxies. Supermassive black holes influence their host galaxies in several profound ways. Perhaps most notably, they are capable of regulating star formation. As material accretes onto a supermassive black hole, it can emit vast amounts of energy in the form of radiation and outflows. These outflows can heat up the surrounding gas or expel it from the galaxy's core, reducing the material available for star formation. This self-regulation mechanism ensures that the galaxy does not burn through its gas reserves too quickly, promoting a more sustained period of star formation and evolution. Moreover, the energy released by the accretion of material onto a supermassive black hole can trigger the reionization of surrounding gas, making it too hot and energetic to collapse into new stars. This process, known as feedback, is critical in shaping the size and structure of galaxies, preventing them from becoming too massive by limiting the amount of cold gas available for star formation. Supermassive black holes also play a key role in the dynamics of galaxy centers. Their immense gravitational pull can influence the orbits of stars in the galaxy's core, contributing to the unique stellar distributions observed in many galaxies. In some cases, the interaction between supermassive black holes and stars can lead to high-velocity stars being ejected from the galaxy entirely, showcasing the dynamic and sometimes violent nature of galactic centers. The formation and growth of supermassive black holes remain areas of active research, with theories suggesting they may begin as smaller black holes that grow over time through the accretion of gas and dust, as well as through mergers with other black holes. This growth process is thought to occur in tandem with the development of the host galaxy, further highlighting the interconnected evolution of galaxies and their central black holes. The structure of the Milky Way, our galactic home, is a marvel of cosmic architecture, embodying the complexity and elegance of the universe's vast expanse. Envisioned as a colossal spiral, our galaxy is a composite of several distinct components, each playing a critical role in its overall makeup and functioning. At its core lies a bulging sphere of stars, enveloping a supermassive black hole known as Sagittarius A*, a silent yet influential force driving the galaxy's dynamics. This bulge, dense and packed with stars, some of which are among the oldest in our galaxy, hints at the Milky Way's ancient history and the evolutionary processes that have shaped it. Surrounding the central bulge is the galaxy's disk, a vast plane extending up to 100,000 light-years in diameter, composed of stars, planets, gas, and dust. This disk is not uniform, but is punctuated by spiral arms, sites of intense star formation and vibrant cosmic activity. These arms, named after the constellations that can be seen from Earth, such as the Perseus and Sagittarius arms, weave through the galaxy, their patterns believed to be shaped by density waves that compress gas and dust, sparking the birth of new stars. Embedded within the disk is the Sun, our own star, situated in a smaller arm called the Orion Spur, about 27,000 light-years from the galactic center. This location offers us a privileged vantage point from which to observe and study the broader structure of the galaxy, although our view is obscured by interstellar dust and gas, making much of the Milky Way a mystery waiting to be unraveled. Encasing the disk and central bulge is a spherical halo, an extended cloud of stars and globular clusters orbiting the galaxy's core. These clusters are tightly bound groups of stars, relics of the Milky Way's formative years, offering clues to its composition and the processes of galactic evolution. The halo also contains the majority of the galaxy's dark matter, an invisible substance that exerts a gravitational pull. influencing the motion of stars and gas within the galaxy and holding the Milky Way together. Additionally, the Milky Way features a complex system of satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere. These smaller galaxies, along with others, orbit the Milky Way, engaged in a gravitational dance that, over billions of years, influences their structure and may eventually lead to their merger with our galaxy. The age of the Milky Way, our sprawling galactic home, is a topic that captures the imagination, offering a window into the ancient past of the universe itself. Through the diligent efforts of astronomers and astrophysicists, using a combination of observational data and theoretical models, we've come to understand that our galaxy is approximately 13.6 billion years old. This remarkable age places its formation not long after the Big Bang, which is estimated to have occurred about 13.8 billion years ago, making the Milky Way one of the universe's older galaxies. Determining the age of the Milky Way involves piecing together evidence from various sources. One of the key methods scientists use is studying the oldest stars within the galaxy. By measuring the abundances of different elements in these stars, researchers can infer their ages. Older stars have fewer heavy elements, as these were formed in the cores of stars and distributed into space as stars died, enriching the galaxy with the materials for new stars. The ages of these ancient stars, many found in the galaxy's halo and in globular clusters, offer clues to the Milky Way's early years. Another approach to gauging the galaxy's age comes from understanding the age of the universe itself, derived from observations of the cosmic microwave background radiation, the afterglow of the Big Bang, and the expansion rate of the universe. By comparing the age of the oldest stars with the age of the universe, scientists can confirm that the Milky Way formed early in cosmic history. The age of the Milky Way not only tells us about the longevity of our galaxy, but also provides insights into the processes of galaxy formation and evolution. It suggests that the Milky Way began forming soon after the dawn of the universe, growing over billions of years through the accumulation of gas, the formation of stars, and the merging with other galaxies. This gradual assembly process, influenced by the mysterious dark matter that pervades the galaxy, has shaped the Milky Way into the spiral galaxy we observe today. Understanding the age of the Milky Way also puts into perspective the cosmic timeline on which astronomical events occur. For instance, the Sun, around 4.6 billion years old, is a relatively young addition to the galaxy, highlighting the ongoing nature of star formation and the dynamic evolution of the Milky Way. The galactic center is a term that evokes a sense of intrigue and mystery, pointing us towards the dense, luminous heart of the Milky Way. This region, bustling with astronomical activity, is located about 27,000 light-years from Earth and houses a remarkable array of cosmic phenomena, central to which is Sagittarius A*, SGR-A*, a supermassive black hole that serves as the dynamo at the core of our galaxy. With a mass equivalent to about 4 million times that of our Sun, Iscar A* is the gravitational anchor around which the galaxy's vast spiral structure coalesces. Surrounding this enigmatic black hole is a bustling environment of stars, gas clouds, and other astronomical objects, all tightly packed into a relatively small volume of space. This region teems with a variety of stars, from young, hot blue stars that blaze with intense brightness to older, cooler stars that have orbited the galactic center for billions of years. The presence of young stars in such a hostile environment, close to a supermassive black hole, puzzles astronomers, as the tidal forces exerted by the black hole should theoretically tear apart the gas clouds from which stars form. Yet, their existence suggests that star formation processes in the galactic center are somehow different from those in the galaxy's less tumultuous regions. In addition to stars, the galactic center is awash with vast clouds of gas and dust, some of which are in the process of being pulled into SGR-A*, while others may be forming new stars. The region is also crisscrossed by filaments of magnetic energy and bathed in the intense radiation emitted by the accretion of material onto the supermassive black hole, creating a dynamic and complex astrophysical laboratory. The area around the galactic center is also the source of various high-energy phenomena, including flares and other emissions resulting from the interaction of SGR-A* with its surroundings. These events provide astronomers with valuable insights into the physics of black holes and the mechanisms of energy transfer in the extreme conditions near a galaxy's core. Observing the galactic center is a challenging endeavor due to the vast amounts of interstellar dust that lie between it and Earth, which obscure our view in visible light wavelengths. However, astronomers have employed radio, infrared, and X-ray telescopes to pierce through this veil of dust, revealing the center's complex structure and activity. These observations have not only confirmed the presence of the supermassive black hole, but have also allowed scientists to study the properties of SGR-A* and its impact on the galactic center's environment. The Milky Way, our grand spiral galaxy, does not exist in isolation in the vast expanse of the universe. It is accompanied by a retinue of smaller satellite galaxies, each with its own unique characteristics and trajectory, yet all are bound to the Milky Way by the invisible tethers of gravity. These interactions between the Milky Way and its satellites are not merely distant, passive relationships, but are dynamic and, at times, tumultuous, playing a significant role in the evolution of our galaxy. Among the most notable of these satellite galaxies are the large and small Magellanic Clouds, visible from the southern hemisphere. These dwarf galaxies, rich in gas and dust, are in a close gravitational dance with the Milky Way, one that has implications for the structure and future of all the galaxies involved. As they orbit our galaxy, gravitational forces act between the Milky Way and the Magellanic Clouds, resulting in phenomena such as tidal stripping, where gas is pulled away from the satellite galaxies. This stripped gas can feed into the Milky Way, contributing to the reservoir of material from which new stars form. Moreover, the interaction between the Milky Way and its satellites is not a one-way street. The gravitational pull of the Magellanic Clouds, for example, has been implicated in the warping of the Milky Way's disk, a subtle yet telling indication of the interconnectedness of cosmic structures. Additionally, these gravitational interactions can spur the formation of tidal streams, elongated trails of stars and gas stripped from the smaller galaxies. These streams, some of which can be traced back to long-lost satellites now fully merged with the Milky Way, provide archaeologists of the sky with clues about the Milky Way's history and its satellite interactions. The Sagittarius Dwarf Spheroidal Galaxy offers another vivid example of these galactic interactions. Currently in the process of being cannibalized by the Milky Way, this small galaxy is being torn apart by our galaxy's gravitational forces. The remnants of this ongoing merger, in the form of stellar streams wrapping around the Milky Way, are a testament to the dynamic nature of galactic evolution and the eventual fate of many satellite galaxies. These interactions are not merely incidents of cosmic violence, but are fundamental processes that drive the evolution of galaxies. The accretion of satellite galaxies brings fresh gas into the Milky Way, fueling new generations of stars and contributing to the chemical complexity of our galaxy. At the same time, these mergers and interactions help to redistribute matter within the Milky Way, influencing its structure and dynamics. Peering into the future of the Milky Way galaxy unveils a narrative rich with cosmic evolution and dramatic transformations. As astronomers gaze through their telescopes and run simulations on powerful computers, they forecast a future in which the Milky Way undergoes significant changes, shaped by the inexorable forces of gravity, the ongoing process of star formation, and impending galactic collisions. One of the most monumental events predicted to occur in the Milky Way's future is its collision with the Andromeda Galaxy. Currently, Andromeda, also a spiral galaxy like the Milky Way, is about 2.5 million light-years away, but is moving towards us at about 110 kilometers per second. In approximately 4 billion years, the skies above Earth, or any planet hosting observers at that time, will bear witness to this grand cosmic merger. As these two galaxies begin to intertwine, their mutual gravitational forces will draw them closer, eventually merging into a single, larger elliptical galaxy, sometimes humorously dubbed Milkomeda or Milkydromeda in scientific discussions. This merger is not expected to be a cataclysmic destruction of either galaxy, but rather a complex dance of stars and gas clouds. Given the vast distances between stars, direct collisions are unlikely. Instead, the gravitational interactions will send stars and planetary systems into new orbits, possibly ejecting some from the newly formed galaxy altogether. The gas clouds within the galaxies, however, will collide, leading to intense bursts of star formation, lighting up the merging galaxies with new stellar nurseries. Following the merger, the center of the newly formed galaxy will be dominated by the combined mass of the Milky Way's and Andromeda's supermassive black holes. These colossal black holes will gradually spiral towards each other and eventually merge, releasing vast amounts of energy and possibly sending ripples through the fabric of space-time itself in the form of gravitational waves. In the long term, the future of the Milky Way, like that of all galaxies, will also be influenced by the life cycles of its stars. As stars exhaust their nuclear fuel, they will evolve through their life stages, with massive stars exploding as supernova and less massive stars shedding their outer layers to form planetary nebulae. Over trillions of years, this will leave behind a galaxy populated by dim white dwarfs, neutron stars, and black holes. The universe's continuous expansion will have a profound effect on the Milky Way's future. Distant galaxies will recede far beyond our observational reach, making the universe appear increasingly empty from our vantage point. However, the gravitational bond between the Milky Way and its local group of galaxies will keep these cosmic neighbors together, forming a small oasis of matter in an accelerating, expanding universe. The formation of the solar system is a captivating chapter in the story of the cosmos, revealing the processes that led to the creation of our sun, the planets, and the myriad smaller bodies that orbit our star. This cosmic tale began around 4.6 billion years ago in a dark corner of the Milky Way, when a vast cloud of gas and dust, known as the Solar Nebula, started to collapse under its own gravity. This collapse was likely triggered by the shockwave from a nearby supernova, which injected energy into the cloud, causing it to compress. As the nebula collapsed, it began to spin, flattening into a rotating disk with the densest material gathering at the center. This process of accretion led to the formation of a protostar at the heart of the disk, which would eventually ignite to become our sun, fueled by nuclear fusion reactions converting hydrogen into helium. Surrounding the newborn sun, the remaining material in the disk began to coalesce. Through a process known as accretion, particles collided and stuck together, gradually building up to form the larger bodies of the solar system. Closer to the sun, where temperatures were higher, metals and silicates were able to condense, forming the terrestrial planets, Mercury, Venus, Earth, and Mars. These rocky bodies are composed mainly of silicate rocks and metals, with Earth being the only one to harbor life as we know it. Further out, beyond the so-called frost line, where temperatures were cold enough for ice to remain solid, gas giants and ice giants began to form. Here, planets like Jupiter and Saturn were able to accumulate massive amounts of hydrogen and helium, growing to enormous sizes, while Uranus and Neptune, the ice giants, gathered their bulk from water, ammonia, and methane ices. The outermost regions of the solar system saw the formation of the Kuiper Belt and the Oort cloud, home to countless icy bodies, comets, and dwarf planets, such as Pluto. These objects are remnants of the early solar system, largely unchanged since their formation. One of the most fascinating aspects of the solar system's formation is the role of Jupiter, the largest planet. Its immense gravity influenced the orbits of other bodies, shaping the architecture of the solar system and possibly flinging some objects into the sun or out into the vastness of space. Throughout billions of years, the solar system has been a dynamic and evolving place, marked by collisions and migrations that have shaped the planets and their orbits. The late heavy bombardment, a period of increased comet and asteroid impacts about 3.8 billion years ago, is one example of the dramatic events that have left their mark on the solar system. In understanding the formation of the solar system, scientists rely on a combination of observational data, computer simulations, and the study of meteorites, which provide direct evidence of the early solar system's composition. These investigations not only shed light on our cosmic origins, but also offer insights into the formation of other planetary systems across the galaxy. The Milky Way, our galaxy, played an indispensable role in the formation of the solar system, setting the stage for the series of events that led to the birth of the Sun and its surrounding planets, moons, asteroids, and comets. This grand cosmic narrative is rooted in the Milky Way's vast reservoirs of gas and dust, its gravitational forces, and the life cycles of its stars, which together fostered the conditions necessary for the solar system's emergence about 4.6 billion years ago. At the heart of the solar system's formation story is the interstellar medium of the Milky Way, a mixture of gas, mostly hydrogen and helium, along with dust. This medium, enriched over billions of years by the remnants of dead stars, provided the raw materials from which the solar system was formed. Supernovae, the explosive deaths of massive stars, played a crucial role by seeding the galaxy with heavy elements like carbon, oxygen, and iron, which are essential for the formation of rocky planets and the development of life on Earth. The Milky Way's gravitational landscape also influenced the solar system's formation. The galaxy's spiral structure, characterized by its rotating arms, is thought to trigger the formation of new stars as it sweeps through the interstellar medium, compressing gas and dust. It's within such a dynamic environment that our solar system found its origin in a dense region of a molecular cloud, where the conditions were just right for the solar nebula, the cloud of gas and dust that collapsed to form the Sun and its planets, to coalesce. Furthermore, the Milky Way's chemical composition, a record of its history of star formation and death, provided a critical backdrop. The particular mix of elements available in the region of the galaxy where the solar system formed influenced the types of planets that could emerge. The inner, rocky planets, Mercury, Venus, Earth, and Mars, formed from materials that could condense at the high temperatures close to the young Sun. In contrast, the gas giants and ice giants formed farther out, where cooler conditions allowed for the accumulation of volatile compounds. The solar system's location within the Milky Way is another aspect of the galaxy's role in its formation. Situated in the Orion Arm, a relatively quiet region between the major spiral arms, the solar system has been spared from the intense radiation and gravitational disturbances that might disrupt planetary systems closer to the galaxy's bustling center. This stable environment has been conducive to the development and persistence of life on Earth, providing a vantage point from which we can observe and study the galaxy and the broader universe. The formation of Earth is a chapter in the grand narrative of the solar system's birth, unfolding over 4.6 billion years ago within the swirling disk of gas and dust known as the solar nebula. This process, driven by the laws of physics and the dynamic environment of the early solar system, led to the creation of our home planet, a world uniquely suited for life as we know it. As the solar nebula collapsed under its own gravity, it spun faster and flattened into a disk. At the center, the sun began to form, igniting its nuclear furnace and casting light and heat out into the surrounding space. In the cooler regions of the disk, far enough from the young sun's warmth, particles of dust and ice began to stick together as they collided, forming clumps that grew into larger bodies over time. These early building blocks of the planets, known as planetesimals, continued to collide and merge, driven by their mutual gravitational attraction. In a process termed accretion, these planetesimals gradually built up the rocky cores of the inner planets, including Earth. This early phase of Earth's formation was marked by intense bombardment as it grew through the accumulation of material, reaching about 60% of its current size relatively quickly in a few tens of millions of years. As Earth grew, its interior heated up due to the energy released from these collisions, along with the decay of radioactive elements within its materials. This heat caused the young Earth to partially melt, allowing it to differentiate into layers: a dense metallic core, a silicate mantle, and a crust on the surface. The formation of Earth's core was crucial for generating the planet's magnetic field, which plays a key role in protecting the surface from harmful solar and cosmic radiation. Meanwhile, the intense heat and volcanic activity released gases trapped in the rocks, contributing to the formation of Earth's early atmosphere. Water vapor, carbon dioxide, methane, and ammonia were among the gases released, creating a primordial atmosphere very different from the one we breathe today. Water vapor in the atmosphere eventually condensed as the Earth cooled, falling as rain and filling the basins that formed on the planet's surface, creating the oceans. The presence of liquid water, essential for life, along with the stability provided by Earth's size, orbit, and its protective magnetic field, set the stage for the eventual emergence of life. Over billions of years, Earth's atmosphere and surface evolved. The emergence of life, particularly photosynthetic organisms, transformed the atmosphere, increasing the amount of oxygen and making it hospitable to a diverse range of life forms. These biological and geological processes have continued to shape Earth, making it the dynamic, life-supporting planet we know today. The emergence of life on Earth, a planet teeming with diverse forms of organisms, is the result of a unique combination of conditions and events that unfolded over billions of years. These conditions, ranging from the planet's placement in the solar system to the composition of its atmosphere and oceans, created an environment conducive to the development and sustenance of life as we know it. One of the most fundamental conditions that made life possible on Earth is its location in the solar system, often referred to as the Goldilocks zone or the habitable zone. This region is not too close to the sun, where it would be too hot for liquid water to exist, and not too far, where it would be too cold. Earth's orbit within this zone allowed for the presence of liquid water on its surface, a critical ingredient for life. The formation of Earth's atmosphere was another crucial step in creating a habitable planet. Initially composed of gases released from volcanic eruptions, such as water vapor, carbon dioxide, and ammonia, the atmosphere underwent significant changes over time. The emergence of photosynthetic organisms, which could convert carbon dioxide and water into oxygen and glucose using sunlight, gradually increased the oxygen levels in the atmosphere. This oxygen-rich atmosphere not only supported the development of new life forms, but also formed the ozone layer, which protects the surface from harmful ultraviolet radiation from the sun. Earth's magnetic field, generated by the movement of molten iron in its outer core, shields the planet from solar and cosmic radiation that could strip away the atmosphere and harm living organisms. This protective field ensures that the atmosphere remains intact and provides a stable environment for life. Earth's geological activity has played a significant role in creating conditions favorable for life. Plate tectonics, the movement of the Earth's lithospheric plates, has led to the formation of continents and ocean basins, the recycling of carbon through the carbon silicate cycle, and the regulation of the planet's temperature. This dynamic geological activity has also facilitated the distribution of minerals and nutrients essential for life, creating diverse habitats and environments. The presence of water in all three states, solid, liquid, and gas on Earth's surface, is another condition pivotal to life. Water is a solvent, facilitating chemical reactions necessary for life, and its unique properties, such as its ability to dissolve a wide range of substances, have been crucial in the development of complex biological molecules. Lastly, Earth's natural satellite, the Moon, has contributed to the stability of the planet's climate by stabilizing its axial tilt, which influences seasonal variations. The relatively mild and stable climate resulting from this axial tilt has allowed for a wide range of ecosystems to flourish over millions of years.